Croeso, welcome again, to the Carlam Cymru revision sessions. And so this session will focus on A-level electronics following the EDUCAS syllabus. I'm Jonathan Williams, I teach electronics at Ysgol Gwendraeth. I'll be doing this session through the medium of English, but I'll be using the Welsh terms as well when I'm talking about certain components. Please remember, if you are writing in the exam itself, a chi'n neud y trwy gyfrwng Gymraeg, mae croeso chi I rhoi'r termau mewn y Saesneg, fe chi ddim yn cael eich cosbi o gwbl. I will try and endeavour to answer any questions at the end of the session. Okay, so if you type any questions in the chat, I'll try and come back to you after that. It'll be recorded, and any relevant resources, will be uploaded at the e-sgol website, in the Carlam Cymru area. The website address is given there, so e-sgol Cymru. If you just Google that as well, e-sgol Cymru, I'm sure the website will come up. And from there, you'll be able to access recordings that have been done in the past. Those recordings from last year and for this year. This is the fourth one in the series. So today I'll be talking about transistors. That's siarad ynglyn â transistors and cyfnod heddi. Session 1 was on logic, session 2 was on timing, session 3 was on op-amps, felly bant ni. Equations which are not given to you in the exam, please remember you have V equals IR. So you've got the V equals IR one. Please remember to use that, correctly. Write it down at the start. Other equations which I'll be using is the power equations. We've got the IV and we've got the I squared R. In the data sheet, the transistor equations are there. You've got the collector current, HFE, the gain, and the base resistor, that one. And that's for the bipolar transistor. And then you've got the MOSFET equation, which is the IDGM, and you've got the VG minus 3. You've also got the power equation for a MOSFET, which is your I squared RDS. So please make a note of those in your data sheets. And away we go. Now then, first thing about transistors and MOSFETs, they will commonly be connected to a potential divider. So a potential divider is basically two resistors. Often you will have a sensor of some kind. So for example, that could be a thermistor, or it could be a light-dependent resistor, which will change the voltage which goes into your transistor. All right. So please remember, the potential divider equation is not given. So the potential divider equation states that the output voltage is the supply voltage multiplied by the resistor that you are using, and then it'll be over, R1 plus the R2. So that is your R1 resistors on top and the R2 resistor. So whatever resistor you want to work out the voltage, that will be the top one that you use. So that is not given, so you need to remember to use it. So I'll give you an example of using it in this case. So what we have here would be the output voltage, and that would be equal to, now in this case, the supply voltage I've got is 15, multiplied by the 560, and then that would be over the sum of the two, which is 240, plus the 560. If you're watching this back on the video, I could pause there, use your calculator, work it out. Practice, please. Answer for that, would be 4.5 volts. I'm sorry about the pen playing up a little bit there. So the 4.5 volts, remember, if this is 4.5 volts on the bottom, then that would mean that the top voltage across that 240 you could work out straight away by doing 15 minus 4.5. So potential divider equation, always handy with transistors and with MOSFETs. Another one which is commonly used with transistors and MOSFETs is the Schmitt trigger. So with a Schmitt trigger, if we just have a quick look at the reminder of how this thing works, basically what you've got with the Schmitt trigger is that you will have a voltage coming into it, and that voltage can vary. Okay, so here's the Schmitt trigger. See the bottom voltage there is varying a little bit, but your Schmitt trigger only gives one value or another one, so it's either higher or low. So if there's any fluctuations, unrhyw newidiadau yn y voltedd, any fluctuations, you can get rid of them, right? So a Schmitt trigger is a device which is used for signal conditioning, okay? So signal conditioning, mae'n neud y signal yn uchel neu mae'n neud yn isel, okay? So it gets rid of things like mechanical bounce, all right, and any fluctuations, large fluctuations in voltages. So it gives you either a 0 or it gives you a 1, okay, feeding into a system. So they are fantastic, basically, when you're using sensors, because the sensors might be fluctuating. So remember that, they like asking that in an exam. So you see the fluctuations there on the blue line, okay, and the red line there gives you the output voltage, which is either a 1 or a 0. So in this case, we've got a potential divider, and then that potential divider is feeding into a Schmitt. Now, with Schmitt, they will give you a rising input and a falling input threshold values. Okay? So in this case, we've got a 3 volts and a 1 volt. So if you've got a signal coming in, okay, what I'd be tempted to do is put in a little line which is showing the 3 volt threshold, and then I put in the 1 volt threshold. Okay, so when it comes to doing the graph for that, then you'll be able to see that when it crosses it, when it's falling, okay, it hits the threshold is 1 volt. So that point becomes very important there. You've also got the rising threshold, so when it crosses at that point, which is there. So what we've got is basically a graph that we can now draw. So this graph would basically be rising at the 2. Okay, it goes up to the 5 volts. And then when it comes to that 4 volts, which is falling, it's been conditioned. Okay, so we've got rid of noise, any fluctuations. Okay, so it's a nice signal which feeds in. So that is the Schmitt trigger. Moving on to the transistor itself. Okay, characteristics of a transistor. I would say things to remember in the exam. Number 1 is that you have a voltage needed of 0.7 to turn a transistor on. Okay, it won't come on unless it reaches 0.7. So this area there is where the transistor is off. Linear region is where the transistor is switching on. You've got current coming down through your collector, and it is a barred region to be in when you're a transistor. You don't want to be there, because what your transistor is now doing, it will dissipate power. Okay, fe fydd yn afredloni y pŵer, dwi ddim yn lle da I fod. Saturation is a good place for a transistor. You've got 0 power again. So with transistors, it's a switching device. Okay, you try to be in saturation. Okay, so it's fully on. Sometimes you will end up in the linear region, but please remember that is barred. They like asking that in an exam. Power in the region, linear region, will be given by IV. Okay, and that is one that you do have to remember. Okay, and the V out would be the output of the transistor itself. So let's just have a look at a transistor in working order. So what we've got in this case at the minute is the voltage, input voltage is going to be changed. Okay, and that is the red line which you're seeing there. Now, once that has reached 0.7, okay, at this point, okay, so we've got at that point there, the transistor has now started to turn on. So you're seeing the output voltage of the transistor is actually decreasing. Okay, we're in the linear region, we're now in saturation. All right, so once we're in saturation in this bit, which is there, the output voltage of the transistor is very, 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 very close to 0. All right, so it's more or less giving you 0 power output on the transistor, which is good. Right, all that voltage when you're in saturation is now given across whatever is on the load. In the case, it was a bulb. Okay, so things to remember: base emitter, okay, voltage. You need the 0.7 in order for the transistor to work. The emitter current is IC plus the IB, okay, but the base current is so small, okay, you can forget about it really, all right, and just assume that emitter current is equal to base current. So points to remember on the transistor itself: you've got the base, you've got the emitter, sorry, the emitter on the bottom, and you've got the collector. Okay, so in the Welsh terms there, okay, you've got the gyda chi'r sail, okay, yn mynd mewn, mae gyda chi y casgledd, so mae still a C am casgledd, a mae gyda chi allafrydd am yr emitter. Right, common calculations you will have to work out is what voltage input will give you basically saturation. All right, so what you will do, you tend to work backwards. So the first thing, you look to see what the conditions are for your collector current. So from the collector current, if you need, for example, in this one, you've got 200 milliamps, you then work backwards. So you'll have the base current. The base current will be worked out by using the equation. IB is IC over HFE. Once you've got your base current, okay, then you can work out basically what voltage will be dropped across the base resistor. So that base resistor is there for a reason, to control the base current. Okay, mae 'na I rheoli on a cerrent sy'n mewn i'r sail. Once you know the voltage which is across that base resistor, add 0.7 to it. So if you add the 0.7, because that's what's needed to switch the transistor on, you can then work out what voltage will make it saturate. So let's look at an example. So in this case, okay, yeah, we've got a potential divider, we've got a sensor, we've got a light dependent resistor there. Just drop this in, light dependent resistor. Okay, we'll do that. As your light level, this is your light level increasing, and basically the resistance will drop as it gets brighter. Okay, so the voltage across that as it gets brighter will get smaller. When it's dark, you've got a big voltage basically across it. So what we've got here is working out the base current. So if you want to rearrange your equation straight away, you got your base current, and your base current is your collector current divided by your HFE. And if you're looking then at numbers, so in this case, your collector current is the 1.5, and your HFE is given as 500. Transistors tend to have a large HFE, that's basically your current gain, okay? Tends to be quite large numbers. So from there, you end up getting 3 milliamps. Okay, so from there, you type in and calculate that to the 1.5 divided by 500. Gives you 3 milliamps. Base currents tend to be very small. There's your check. Okay, so now we're looking at the value of the base resistor. We're going to work that one out. So the first thing is that you've got your V of the resistor, which is going in, and that would be 5.2 take away 0.7. Why? Because 5.2 is what is coming in. Now remember, the transistor is going to take 0.7 volts. Okay, so there's the voltage which is across it. You've got your base current. There is. So that base current is going to come in. There's your 3 milliamps. You're going to have a go, type that into a calculator, working that out. Okay, that will give you 1,500 ohms. Right, here's a transistor again, okay, with the characteristic graph. So I'll just remind you, the transistor is off in that region. Here's your linear region, yr ardal llinol. Chi ddim eisiau bod na. You don't want to be in that linear region. You've got power dissipation. And there's your saturation. Okay, so if I was to drop a line from there, where it starts to go into your linear region, that would give you the 0.7. Okay, where does saturation occur? It happens at that point, which is there. It happens to be 5.5. 5 volts. Okay, so from there, you could work out basically what base current would be. So base current is your collector current over HFE. That's the first thing I'll go for. Looking at the question itself, okay, I can't see anything about HFE in the question. So I'm going to have to think about another way of doing it. And if I look at it, I've got 1.2 amps coming down through the heater. So in saturation, I would have basically 15 volts across that heater itself, right? And I've got a 1K resistor. So I know saturation happens at 5.5 volts. So if I've got 5.5 volts coming in, I know the transistor is going to take 0.7. So I could work out the voltage, which is across this resistor, which would be 5.5 minus the 0.7. And then if I know basically the size of the resistor, I can work out by using the equation for IB. I is V over R. Okay, so we're back to that one. So I've eliminated the first equation, can't use that one. Okay, so I could do that one by doing the 5.5 minus the 0.7, which is coming in. Okay, and divided that by the 1K resistor. Okay, if you want to try that on your calculator, okay, that will give you 4.8, and that's milliamps. Okay, so sometimes, yeah, you could try an equation, you realize you don't have something, okay, and then you try another equation, look to see what the values you've got. You're looking for the HFE, rearrange your equation so HFE is equal to, okay, so HFE would be equal to, well, IC and you divide the IC by the IB. So in this case, we had 1.2 amps coming down, got the base current, which we just worked out as 4.8 milliamps. I'm going to try that in a calculator if you're watching on video. Okay, we'll give you a gain of 250. You know, in the right ballpark, 250 is quite a big number. Okay, typical HFE values. Right, you're looking at calculating the value of Vn. Right, so looking back at this one, you've got basically that potential divider being used again. Right, so I'm going to dive in and I'm going to use the potential divider in order to work it out. So in this case, it's going to be the 15 times 250. And that's going to be over the 1,000 plus the 2,000, sorry, 250. Okay, just looking back where those numbers have come from. Right. There's a supply voltage. This happened to be 250. So it's that times the bottom resistor over the sum of the two. There's your potential divider. Use the graph. Okay, if they're going to ask you to use the graph, right? Always handy basically to show the examiner that line coming up. Okay, going over. There it is. You've got the 8 volts. Okay, now this is asking about the MOSFETs. We'll come to those MOSFETs in a minute. But basically, what effect does this have on the transistor? Now, if you're looking at that 8 volts, you're basically in this linear region. And what we say is you don't want to be in the linear region because you can basically back yourself up by using the equation, right? If you're in that linear region, you have a collector current and you have an output voltage across that transistor, which means you are going to dissipate energy. You are going to have basically a power value, power on that transistor itself, and which is going to make it hot. Okay, so heat will come off from that transistor. If you use the MOSFET, now the thing with MOSFETs compared to transistors is that they have a much sharper linear region. So if I give you an example, a transistor would have a graph, looks like that. With a MOSFET basically has a much sharper linear region. Okay, so that linear region, much sharper, so you're less likely to be in it. So basically the MOSFET will have saturated a long time before a transistor will. Okay, so you will dissipate less power. Okay, what you got here again, you see the same old questions coming up. You're asking about the base current. So we're going to go in with the base current of IC over HFE. You've got your buzzers rated at 120 milliamps. So that means there's the buzzer, symbol for buzzer. You have to know that one. There's the 120 milliamps. Okay, and the HFE is given to you in the question as well. That will give you 1.5 milliamps. Value of the resistor again. Okay, so you're going to do R. You're looking for V over I all the time for value, anything to do with the resistor. So the voltage. Now in this case, you've got 3.4 volts coming in. So if I know I've got 3.4 volts coming in, transistor is going to take 0.7 every single time. Okay, and then you've got the base current, which you've just worked out. There's your 1.5 milliamps, which is times 10 to the minus 3. Okay, work that one out. You would end up with 1,800 ohms. So it asks you to draw the graph for it. Right, I'm going to go straight in with a 0.7 because I know 0.7 is basically where my transistor started to come on. Okay, so up until that point, it was off. So the output voltage would be 9. Sounds weird. Basically, transistor, there's your V output. If your transistor is off, all that voltage basically, because there's no current coming down, that voltage would be at 9 volts at that point. Right, so it's on 9 until then. Once you've got that 9 volts, right, and the transistor comes on, you're going to go into the linear region. But then we know saturation happens basically at 3.4. So I'm going to mark it in, put a nice little cross in, and then what you can do is join those two crosses up with a ruler, obviously. Okay, there's your linear region. Okay, and there's the bottom line. Right, use the graph to determine the value of V out. Okay, when V in is 2.5. So I'll be looking at the graph itself. I'll be looking at 2.5, marking it off, showing the examiner, okay, that I'm using the graph. So I'll be drawing that line up, marking it across. Okay, so from there, the answer is 3.6. That's the key thing. If you see the terms defnyddioch y graph, use the graph, show the graph by using those lines. Right, and here we go with the power dissipated. Right, so the power dissipated in a transistor will always be IV. Okay, IV, remember it. So the current which is going in there would be the 80 milliamps. Just coming down to the collector, lawr trwy'r casgledd. So you take the 80 milliamps, so it's 80 times 10 to the minus 3. And you've got the V output, which you've just got, is 3.6. So in this case, you've got a power output of 0.28 watts. They like asking you to maybe add things to the transistor. So in this case, they were asking you, right, we wanted to get a light level sensor in, which will turn this buzzer on, okay, once it reaches a certain level, all right? So what we're going to do, we're going to put in light meter, will be the resistor, with 2 lines shining on it. Okay, setting up the potential divider. Okay, and there you go. When the light level gets too low, the light level sensor comes on. So you just remember, that light level sensor that could be on the top. Right, so what are we going to do? Just give you a quick reminder. The shape of an LDR, light dependent resistor, is that the resistance is high when it is dark. So if it is dark, that R is a big value, which would mean that you've got a big voltage. So big voltage is going to turn that transistor on. So basically, it's going to give you basically a warning, right? So as it gets lighter, the resistance decreases. Decreasing resistance would now mean you've got less voltage. Less voltage means you're not going to turn your transistor on. Okay, bang. Your buzzer is off. Okay, so just remember those little facts. Okay, which takes us on to the world of MOSFETs. Okay, MOSFETs were designed after bipolar transistors. So they're a more modern thing. Now, the big thing about a MOSFET is, please remember, they are voltage driven, right? So you don't basically have any current coming in through the gate. Gate are adoy. You've got a drain on the top, a drain, and you've got the source. Mae gyda chi'r ffynhonnell fyna. Felly mae'r current sydd yn dod mewn i'r MOSFET, mae fe yn zero. All right? They like asking that little question in an exam. So remember your equation basically from the data sheet. You will use that to work out what your drain current is. So yeah, you tend to have a big drain current, but it all depends basically on how much voltage you've got coming in between your gate and your source. So basically your input voltage. Now MOSFETs are absolutely awesome when they're connected to logic gates, okay, or a potential divider, because from a logic gate, you've got voltage coming in, boom, straight into your MOSFET, you turn it on, right? Same thing with a potential divider. You've got a nice voltage where it comes in at a certain point, okay, which will turn your MOSFET on. When it comes to projects, building things, I'm a big fan of MOSFETs as opposed to transistors because they're voltage driven. Okay, here we go with an example of a MOSFET. So what we've got here is the voltage rising. Okay, so you need about 3 volts, right, in order to turn. There's a turn on voltage. You need 3 volts to basically turn on a MOSFET. But then, as I said, linear region, rather than is really sharp, and so it saturates really quickly. Okay, let's fuss with the MOSFET. There's no base resistance, okay, at all. You got that voltage coming in, massive input impedance because you've got that current then, which is 0. So there's the potential divider, which usually feeds it. So there's the use of an equation. Okay, so in this case, you're always looking maybe what is the value of voltage and current needed to turn something on. So in this case, we've got a bulb, we've got a 12 volt supply, that 12 volts, and you've got 4 amps. 4 amps basically will be the drain current. GM, okay, that is your transconductance, right, measured in Siemens, invented by the Siemens company. That GM basically is the gain. It's the equivalent of HFE, okay? Tends to be small values. Right, so in this example, which leads up to using a MOSFET, right, got a potential divider coming in again. Okay, so in this case, we've got a 2.3K on the thermistor. I'll just give a quick reminder on that one. The voltage across that will then be equal to the supply voltage, which is 5. Right, and you've got the 2.3 of the thermistor itself, and then you add the 10K to the 2.3. Okay, so from there you would end up with 0.9 volts coming in. Right, now then, as I said, very often, if you've got a potential divider of the sensor, that voltage there is going to fluctuate, right? So you're going to have a voltage which is doing all types of crazy stuff, right? So in order to get like a decent voltage, either on or off, if you're feeding MOSFET, you put it into the Schmitt. So the Schmitt is basically, here we go, signal conditioning, all right? Asks you sometimes, what's the use of a Schmitt? Cofiwch, mae fe yn neud voltedd I fod yn lle un uchel neu initial. Okay, it makes it high voltage or it makes a low voltage. Here's your graph with a Schmitt. So from graphs like this, remember what happens is you got that bit, which is your upper threshold for increasing. So your voltage is increasing, bang, it's inverting. Okay, and then you got your low threshold, which is there. Okay, so your upper threshold in this case is 3.5, and then your low threshold, okay, where it kicks back up, okay, is on 1 volt. So signal which is coming in, oh dear, it's a fluctuating signal. Are we going to clean it up, or are we going to put it into a Schmitt? All right, so what we're going to do, I like the way I just worked it out. Threshold values are on the 1, okay, and on the 3.5. So if those voltage values are going in, what I'm going to end up with, right, so I'm looking at, there's the upper threshold, doesn't cross it there. Yes, that point is important. It's a decreasing voltage going over the lower threshold, so that's going to be important. Also, that point there now is important, because that's the voltage rising. That voltage is rising past the upper threshold. So what I'm going to end up having is signal which goes high. Okay, and this one gives an output voltage of 5. Basically, it'll go low on your upper threshold. So there's the signal conditioning, nice and clean. Okay, so here we go with the use of the MOSFET. Potential divider, sensing, Schmitt is cleaning. Or one thing, yeah, mentioned this in a couple of exams, is you have basically something called a protective diode. Okay, now they're always connected on the collector in a transistor and on the drain. Basically, when you switch off a device which has got a transistor in it or a MOSFET, what you can have is basically something called a back EMF. So those can sometimes damage anything which is connected on the load. If you've got a motor, try makes it go in the opposite direction. So that diode gives you basically a path for when you switch off for something creating for something which has got a back EMF, which might have current going back up through it. Okay, so protective diode, they like asking that for you to add it to the diagram itself. So in this case, it's now asking us to work out what is the GM value, okay, which would basically be able to give you certain currents. So in this case, I'd be quoting the ID is equal to the GM. And then we've got the VGS minus the 3. Apologise for the use of the pen here. Something crazy happening. So I'm just going to go up here a little bit more space. So the drain current in this case rated at 5 volts, 3 amps to the solenoid. Solenoid is a coil. So I'll be setting up by 3. GM is what I'm going to work out. By VGS, okay. So how much voltage have I got coming in this case? Right, I got 5. Okay, because that's what the Schmitt basically is giving me. It's giving me 5 volts. So I've got 5 volts coming in. And then it's minus the 3. Right, so it's a case of rearranging that. Easiest way probably would be just doing times 2. So I'll give you 3 over 2. So the GM then be 3 over 2, which is 1.5 S. Okay, that's standing for Siemens. Okay, here we go with another MOSFET. So looking at the conditions, basically the solenoid in this case needs 10 amps, it needs 25 volts, and it's being driven by a logic system. Okay, that's the advantage of it. Right, they like giving you a data table, okay, to do with MOSFETs. The important thing with these, I would say, is that one, RDS. So when your MOSFET is on, you have got a current coming down through there. Now, your MOSFET basically is going to dissipate power, right? And the equation which is in your data sheet is basically P, when it is on, will be IDS squared times R. So that R value, RDS, is the resistance between the drain and the source when your MOSFET is on. So inside the MOSFET, there is basically an internal resistance. It's small, okay, but it is significant. Basically, you will use that as your R value to work out the power dissipated in it. So here we go. It says add a diode. Okay, so diode is going to go basically on the collector. Doesn't matter which side of the solenoid you put it, on the left or on the right. That doesn't matter at all. Okay, calculate the value of the VGS. So you set up your equation. So you got your ID. Okay, always worth just writing down the equation. Sometimes you might get a mark for it in an exam because you've identified which equation to use. Right, so in this case, you're looking for the ID. I can see the solenoid needs a 10 amp. So that 10 amps. Substitute the values in. Again, okay, showing just the substitution of values in an equation, you get a mark for it. Okay, so in this case, we've got a GM from the data table. Okay, there it is. It's 2.5. Now the VGS is what we're going to work out in this case. -3. Just remind you that 3 comes from the fact that MOSFETs need at least 3 volts in order to turn them on. Now it's just a case of rearranging. So I would tend to basically n divided by the 2.5, take the 2.5 over, and then I would add the 3. Okay, which leaves the VGS on its own. Okay, so from there, substitute in, that would give you the 7 volts. Okay, and then finally, working out the power dissipated in a MOSFET. So this is the equation that you get from your data sheet right at the start. Okay, so what you got is you quote the equation. So you got your ID squared as your drain current. And then you multiply it by your RDS because it is on. So looking at the numbers, I got an ID in this case of 10 amps coming down, squared. And you got a RDS on of 0.12. Okay, doing that, you'll end up with a power of 12 watts. So 12 watts, you know, is quite a lot of power when it comes to a MOSFET. So when you're building MOSFET circuits, you might want to put a heat sink in sometimes to take heat away from it, right? You can't avoid it. Yeah, so even when it is on and in saturation, basically you've got power. Okay, so that is basically the revision of transistors and of MOSFETs. So as a quick summary of going over things again, things I would tell you, yeah, please remember them, is number 1, okay, you got your V equals IR, write it down at the start of the paper. Okay, you got your power equations, your IV, your I squared, R, and your V squared over R, you need to know those. Okay, there is your potential divider equation, which we've been using quite a lot today. They will come in handy all the time for working voltages off. Okay, you got your data sheet, know where those equations for transistors and where they are for a MOSFET. Important things to remember, Schmitt triggers, all right? Schmitt are used for signal conditioning, okay? Signal conditioning means any fluctuations in the newidiadau and a voltage, any changes in the voltage, okay, you will clean it up. So, for example, with mechanical bounce, we've got switches, okay, which will tend to make voltages vary. Gets rid of those, or any fluctuations in sensors, a Schmitt trigger. You got that one. Know your threshold or how to do a graph for your Schmitt. Okay, put those lines in the graph, always helps. Know that a linear region is a bad area, okay, to be in a transistor. Why? Because you will dissipate power. Your transistor will get hot, okay? Don't want to be in that area. That power equation, P equals IV. That's the one you have to remember. Know basically, yeah, look to see what your conditions are, right? When you've got a transistor in saturation. So you'll have a load, that load will have a certain rating of voltage and current. That's what it needs when it's on saturation. 0.7 of a volt is needed to turn a transistor on, okay? Once it is on, there'll always be 0.7 dropped. So whatever you got on the base resistor, take the 0.7 volts away from it to get the voltage across that base resistor. Gains, HFE of transistors tend to be quite large, 100 up to 500. Yeah, they can go into 1,000 sometimes, okay? Work backwards in order to work out what saturation values are. Know your graph, know that the area there is when it is off, you've got your linear region, and you've got your saturation level, which is on the bottom. With the MOSFETs, okay, know basically your gate current is 0, okay? Ideally, it is 0. Your gate to source of voltage, which is coming into, okay, into your transistor, sorry, into your MOSFET, okay? Usually connected to a logic system, okay, because the logic will give you that basically a VGS value, which is quite big. 3 volts is normally needed to turn a MOSFET on. GM is your gain, okay? So basically equivalent of the HFE. Won't say current gain because it's more of a voltage gain more than anything. And that concludes basically the main things for transistors and for MOSFETs. Okay, so thank you for that.